Okay, so this chapter is organic chemistry, the chapter of alkenes and elimination reactions. Okay, you have to include the carbon-carbon double bond in the naming. So you start with 1, 2, 3, 4, 5, and then this is your substituent. So the name for this compound would be 2-ethyl-1, because the 1 is where the carbon-carbon double bond starts on, pentene. And you do not have cis-trans isomerization because this is a CH2, and on that CH2 the hydrogens are both the same, so you don't have to worry about a Z or an E. Going to the next problem, we have 1, 2, 3, 4, 5, so we have a pentene again, and this is our substituent. So this compound would be named 3-ethyl-2-pentene, ENE. And once again, you don't have to worry about cis-trans isomerization because on this carbon of the carbon-coupled double bond, you have the same groups, which are both ethyl. So there's no cis and trans isomerization. Okay, the next compound is a triene. 1, 2, 3, 4, 5. No, let's name it the other way. Okay, so we should start from this end. 1, 2, 3, 4, 5, 6, 7, 8. So we're looking at 8 carbons. So we're looking at octatriene. So there's the triene. There's 3 of them, and it's on 1. It's on carbon number 3 and carbon number 5. So 1, 3, 5, dash. And then your substituents are the methyl on the 2 and the methyl on the 6. So then before that you do 2, 6 dash dimethyl. And you don't have cis-trans here because that's a CH2. So then you look at the 3. You do have cis-trans on the 3, and you do have a cis-trans isomerization on the 5. So 3 and 5 are going to need to be an E or a Z. So we're going to fill in those blanks here. And when you look at this, you look and you see what's not drawn here is a hydrogen. So this gets a number 1 priority. And then the hydrogen is not drawn here, so we draw that. So the number 1 priority would be over here, and that is across the double bond. So that would be trans. And if you remember, trans is E. So on the 3, we have an E. And then we're going to come over to the next one, this number 5, and we draw on the hydrogen there. So the 1 is on this side of the double bond, and then on this one we have a methyl or an ethyl, so the higher priority is the ethyl, and they're on the opposite side, so that is also an E. Okay, going on to the next problem. We have 1, 2, 3, 4, 5, 6, 7. So 7, so it'd be 3-heptene. And our substituent then is this ethyl group on the carbon number 4. So 4-ethyl-3-heptene. And then do we have cis-trans isomerization? Yes, we do. So we draw in our hydrogen here. This ethyl is group number 1. Then we have an ethyl or propyl. So the propyl is going to get the 1. They're on opposite sides. It's carbon number 3. So we would write before this in parentheses 3 trans, because they're on opposite sides, 3E. Okay, going to the next reaction here, we have a cyclo compound. We've got to give the higher priority to the carbons in the ring here. So we're going to count this as 1, and we're going to go clockwise to give it the lower numbering. And this is a cyclo hexyl group is our substituent. So we have cyclo, hex, and we have 1, 3 diene. Okay, so it's a cyclohex 1,3 diene, and we don't have to worry about cis or trans because you have a 6-membered ring. It's going to be cis, and then you have 1, cyclohexyl, and that's your substituent. And the last compound here, we're going to start numbering here closer to the chlorine to give our carbon-carbon double bond the lowest number. 1, 2, 3, 4, 5, 6, 7, 8. So that's 1, 3, 5 dash octatriene. So there's 3 double bonds there. Our substituents are a methyl and a chloroethyl. So we'll do 3 dash chloroethyl dash 6 methyl for that, and that's alphabetized. The C comes before the M. And then we have to look at our cis-trans isomerization. Carbon number 1, because that's a CH2, we don't have cis-trans there. Carbon number 3, we do, and this is going to be your number 1 group. Actually, this would be considered the number 1 because you have a methine there, CH. So that would be number 1. And then here you're going to have to draw in your hydrogen ones across the bond. So that would be 3 trans, so 3E, comma. And then go to the next one here. Draw in your hydrogen, so one's on top. And then the ethyl here. So that is 5E. Okay, so on this problem, you're to label either Z, which is cis, you have to memorize that, E, which is trans, or neither. So let's just assign these real quick. Between the methyl and the hydrogen, this gets a 1. Between the chlorine and the carbon, this gets a 1. The ones are on opposite sides of the carbon-carbon double bond, so this would be trans. That would be E. Going to the next one. Between the chlorine and the hydrogen, chlorine gets a 1. The methyls are the same, so this is neither. Going to the next one. Between the phenyl and the phenyl gets the higher priority. Between the ethyl and the ethyl gets the higher priority. And that would be on the same side, so that would be a Z. And then this one here, between the methyl and the hydrogen, the methyl gets the higher priority. Aldehyde here, CHO is the aldehyde. Aldehyde has a carbon oxygen double bond, so it gets the higher priority because it's bonded to 2 oxygens, where this carbon's only bonded to 1. They're both on the same side, so once again, that's cis, which is Z. Okay, draw and name all stereoisomers of 3-chlorohepta-2,4-diene. So let's just start drawing these. We have to have 7 carbons. 1, 2, 3, 4, 5, 6, 7. And then we can just start from left to right. The 2, and so that's 2, 3, there's carbon number 4, and then on the 3 you have chlorine. So what would this one be? We'll look at the 2 carbon, and this will be your higher priority, and on the 3 carbon, this would be your higher priority, the chlorine versus the carbon. So this one is 2Z. Z, remember, is cis. E is trans. And then you go to carbon number 4, or I'm sorry, carbon number, 4, and you can draw your hydrogens in there, and you'll see that this is your higher priority, and then the higher priority over here is on the other side. So this would be trans, so 4E. Now, to draw these, you can draw the same way here with the chlorine, and then this one would be the same here. Just drew this the same. So this is still 2Z, but this one now, the hydrogen's here and the hydrogen's here. So these are on the same side, so this would be 4Z. And if you want to draw the other isomer, you're going to have to draw the chlorine on the other side, and then you can draw it like this, whereas you can see that your chlorine's here and the methyl's here, so this would be 2 trans, 2E, and then on this side you can draw your hydrogen in, and you see that you have this group, draw your hydrogens in. These are 4E because they're on the opposite side. So then to draw the other isomer, you just draw the 2E again, and this time you draw the hydrogens on the same side. So if you were to draw the hydrogens in, you would see this is also 4Z. And that should cover all of them. Okay, so on naming these, we need to draw the pentene, 1, 2, 3, 4, 5, and then the carbon-carbon double bond is on the 1. This is neither because this is a CH2, so you're done. You don't have cis or trans. 2-propentene, so you have the carbon-carbon double bond on the 2, 1, 2, 3, 4, 5, and this would be your trans because you have the hydrogens on opposite sides. So then if you want to do your cis, 1, 2, 3, 4, 5, this would be your cis. Hexane, 1, 2, 3, 1, 2, 3, 4, 5, 6. The hydrogens on our opposite sides here, so this is going to be your trans. And then to do the cis, 1, 2, 3, 4, 5, 6, and that would be your cis. Okay, so our slides cut off some of the problems, so we'll just write them in. 1,1-dibromopropene. That's 3 carbons, 1, 2, 3. The 1 is the carbon-carbon double bond is on the 1 because it's not specified here. And then dibromo is on the 1, 1,1-dibromo. Since those are the same thing, it's neither cis nor trans. Excuse me. I have a cold. The next one that we would write in is 3-chloropenta 2,4-diene. So 1, 2, 3, 4, 5, 6, 7, and put the chloro on the 3. This would be cis, and then actually it'd be 2Z, 4E, and then try to draw the next one. And I'll just draw these for you, and you can apply what you know and check your work. 2E, 4E, and then this one here is 2Z, 4Z, and then this one is 2E, 4Z. And the last one we have, yeah, that was the last one. Okay, so go to the next. For each alkene, indicate the direction of the dipole. Okay, so the first one you need to do is draw cis-1,2-difluoroethene. So this is your cis, or trans 1,2-difluoroethene. When you draw in your dipole, fluorine is more electronegative. So fluorine has its lone pairs, and it's going to pull the electron density towards itself. And so the overall dipole for the cis will be in the upper direction. Here, because of the symmetry, they're going to pull equal and opposite in magnitude, so your dipole is going to be 0D. So this cis has the larger dipole. Okay, going to the next problem. Same thing with the dibromoethene. You're going to see the same, but versus the trans. We got a different one here. We have butene. So trans 2,3-butene. But what's happening here is the methyl groups are going to be donating. The bromine is going to be pooling. So in these, you just have it in one direction. So once again, I think that the cis would have a larger dipole, because the symmetry, you would cancel these out. So this could possibly be 0 dipole moment. And the problems not shown on here are, we can't see, let's write it in, would be the 1,2-dibromopropene, cis and trans. So actually, I think that's not right. 1,2-dichloroethene, or cis 1,2-dichloroethene. So 1,2-dichloro. Oh, we have dibromo and dichloro. Dibromo, dichloroethene. So we have the bromo on the 1,2, and you have the chloro on the 1,2. And what's going to happen here is the bromo is going to pull, and the chloro is going to pull. And which one's more electronegative, the bromo or the chloro? I think the chlorine would be. So you get a little dipole in the bottom direction versus the one with just the chlorine, the dichloro. You get more of a pull in just one direction. So the cis 1,2-dichloroethene should have a larger dipole. Okay, this one says predict the products of the following reaction. Okay, this is one of those things where you got to look at your base. You have a tertiary alkyl halide. Now, alkyl halides either go SN1, SN2, E1, or E2. You have a strong base and you have a tertiary alkyl halide. All E1s and E2s, tertiaries, are more reactive than secondaries, are more reactive than primary. They follow the same alkyl halide classification. So you got to look at your base, okay? So you got to classify your base. You're either going to have a strong unhindered base. You got to memorize what these are. You could have a strong hindered base, and you could have a weak base. And just using the methyl group, a strong unhindered base would be sodium methoxide. A strong hindered base would be sodium tert butoxide. And a weak base would just be methanol. No negative charge there, okay? So then you got to look at your carbons next to the carbon bonded to the bromine. So which ones are those? It's this carbon, and this carbon. So you have three neighbors because you have a tertiary alkyl halide. And it's going to abstract, you're going to have elimination, and obviously we have strongly unhindered, so this is an E2. Strongly hindered would be also an E2, and a weak base would be an E1. E1s always give you a carbocation intermediate. Strong hindered would give you a Hoffman product. Strong unhindered is going to give you the Zatsev's product. So we have a strong unhindered, so let's just write SU, strong unhindered, and so we're going to get a Zatsev's product. So we need to abstract the proton that's going to give us the most substituted product. So it's going to be a proton here. You can go with this one or the other one. And we have three arrows because bromine's going to leave. And then we draw that product, CH3. And as you can see, you have 1, 2, 3. This is a hydrogen. This is a tri-substituted product. So that would be your Yatz's product, and it would be the more substituted. Show how you would prepare cyclopentene for each of these compounds. Okay, so they're asking what's your starting material. So draw in cyclopentene, and there's the goal. So how would you prepare cyclopentene from these starting materials? So it really wants to know the base. What base are you going to use? These are dibromo or reagents. Dibromo, cyclopentyl bromide. So let's just start with the first one. Dibromo, cyclopentane. So here's bromo, and here's bromo. 1, 2. Okay, so this is a flat compound. Bromine is above and below. We haven't done this reaction yet, but this is a dehydrogenation. And so to remove 2 bromines, the reagent is sodium iodide and acetone. And it's pentane. And I was wondering about that. So, because you gotta, when it says trans, one's got to be up and one's got to be below the ring. So sodium iodide has a great affinity for bromine, and so the iodide will actually bond with bromine and will eliminate. So this will be cyclopentene. So the iodide will go and take away bromine, and those electrons will then make this bromine a good leaving group and push it out to make your alkene. Okay, the next one is cyclopentyl bromide. So this is what? This is a secondary alkyl halide. So a secondary alkyl halide, it doesn't matter what base we use, so we can just use sodium ethoxide or sodium methoxide. And so this is your carbon-bromine bond. So you look at the neighboring carbons, and you're going to remove one of those hydrogens. You will get Yatsev's product, which is the more substituted, but in this case, you can only get one product, and that's the desired product, cyclopentene. Okay, the next reaction, it says cyclopentane. So how do you do this from cyclopentane? Well, you got to add a halogen in there, and this is free radical halogenation. We did this in chapter 4, where it's going to generate the bromine radical, and then the bromine radical can abstract a hydrogen to generate the free radical. And remember the propagation where this will then brominate. This is how you have to incorporate a bromine in alkanes. Alkanes are non-reactive. And then once you get an alkyl bromine, then you can just do the reaction you did above with sodium methoxide and put in your hydrogens here, and the methoxide will go and abstract the hydrogen and give you the cyclopentene. Okay, our slides got cut off again. Predict the products formed by sodium hydroxide promoted. Okay, so these are our compounds. So 1-bromobutane. So let's draw 1-bromobutane and sodium hydroxide. This is a primary alkyl halide, and you just look for the neighboring carbon. So this is your carbon bromine bond. So you got to look at this neighbor. You only have one neighbor because it's a primary. So sodium hydroxide will act as a base, deprotonate, and you will get an E2, and you'll get the more substituted Yates product. Yates. And 1, 2, 3, 4. So count your 1, 2, 3, 4. So that's actually you get the more substituted, but you only get, yeah, so in this case you can only get one because you only have one neighbor to choose from. You have one neighbor carbon, it's a primary, so you can only get the one product. The next one is 2-chlorobutane. So let's draw 2-chlorobutane. There's 2 butane. Chlorobutane. And you're going to react this with sodium hydroxide. Once again, you have a very strong base, so these are all going to be unhindered. You have a strong, unhindered base, it's all going to be Zaitsev. Okay, strong, unhindered, it's going to be E2 Zaitsev. So you have a secondary alkyl halide. So you're going to have two neighbors. So you're going to have this neighbor and this neighbor. You want to abstract the hydrogen from the more substituted neighbor. So in this case, this neighbor, do your 3 arrows, chlorine leaves, and you get the di-substituted product as your major product. The other one would be to abstract a hydrogen there, and this is your minor product. This is your major. The more substituted Zaitsev's rule. Let's see, do we have any more on this? Okay, on this problem, what halides would undergo dehydrogenation to give the following pure alkenes? Okay, so let's draw the alkene. And this is 1 hexene, so 1, 2, 3, 4, 5, 6. And basically, 1, 2, 3, 4, 5, 6. This, you could just use a primary alkyl halide and sodium methoxide, which is a strong, unhindered base, so it would give you the Zaitsev's product. You look for your neighboring carbon hydrogens, which are next to this carbon. As you can see, that base would deprotonate that, and the bromine would leave to give you 1 hexene. Isobutylene. So draw isobutylene. It's really a bad drawing of isobutylene, so let's try again. We can do better. Okay, so isobutylene, you want the alkyl halide. So once again, we'll just make a primary alkyl halide, use sodium methoxide, which is a strong unhindered base, and the neighbor, this is your carbon that's bonded to the bromine, so your neighboring carbon would isobutyl, 1, 2, 3, 4. The neighboring carbon would be this one here, and you can imagine that sodium hydroxide would deprotonate that to give you your alkene. 2-pentene. So we got 5 carbons, 1, 2, 3, 4, 5. And on carbon number 2, we have our carbon-carbon double bond. Our halogen then, we want them more substituted. So you just do the secondary alkyl halide here, and you could still use sodium methoxide, strongly unhindered base. It's going to give you, it can take away this proton here, and then the bromine would leave to give you your product. Okay, the other compound here is methylene cyclohexene, which is this compound, and the alkyl halide then would be, you could just do the primary alkyl halide and sodium methoxide. Okay, so this problem here, we had some technicality difficulties. So for some reason we can't erase this, and my battery went low, so now I don't have a free board. So we're just gonna have to make do with all this scribbling already on here. Okay, predict the dehydrohalogenation products that result from the following alkyl halides are heated in alcoholic potassium hydroxide. Okay, so we're going to focus on the major product. Something else you can't see here is here's our starting material. So I will redraw these and react them with potassium hydroxide. So this is our first product, and you got to find your neighboring. So this is your carbon that's bonded to the bromine. You got to look for your neighboring carbons. So this is a secondary alkyl halide, so therefore it has 2 neighboring carbons. You're going to deprotonate. You're going to deprotonate the more substituted carbon so you can get the major product. So KOH is a strongly unhindered base, and you're going to get the Yacht-Says product. So it's going to deprotonate, and those electrons are going to make the bromine leave, and your product then will be this tri-substituted alkene. We're looking at the next product here. See, you have, there's your carbon, and it's a secondary alkyl halide. So you look at your neighbors right here and here, and you're going to deprotonate this carbon. So KOH will deprotonate that, and the bromine will leave, and your product then would be this tri-substituted. Actually, looking at the first one, you had another one here. Okay, so this was actually tetra-substituted. Once again, I apologize for the technical difficulties, but we'll just push through this. Here, you have a tertiary alkyl halide. So that means you have 3 neighbors. So you look at this carbon, and this carbon. This carbon is your more substituted carbon, so potassium hydroxide will deprotonate that, the bromine will leave, and your product would be a tri-substituted alkene. Okay, now let's see. Okay, this over here. When you have these cyclohexane rings, you have to draw the chair conformation. So we're doing this product here. And you need to have the leaving group, the chlorine, and it has to be in the axial position. So we can make this carbon here the chlorine. And you can see that it's going back, so that's going down, and the point here is going down, so that's axial down. Now, the methyl is this carbon here. It's right next to the chlorine, and that would be going up. And because these alternate up, down, that would be chlorine up. And then you go to this next carbon here, and this is pointing up. So what's axial up? Well, it would be the hydrogen because the hydrogen's coming at you. And then that means equatorial down is the deuterium. Deuterium is just an isotope of hydrogen. Now, when you do the potassium hydroxide, the elimination, the E2, it's stereospecific. That means it has to be 180-degree anti-paraplanar. Okay, so what does that mean? That means you can only abstract you need to have the leaving group in the axial position. You can only abstract the hydrogen that is 180 degrees dihedrally angled to the leaving group. So this hydrogen gets deprotonated. Those electrons will go here and push the chlorine to leave. So then when you redraw this, you see you haven't touched the carbon with the chlorine there. Now your chlorine's left here, and you have a double bond, and the deuterium is out. Now this is flat. This is sp2. So when you draw the two-dimensional, you draw your deuterium there, your D, and then you draw your chlorine going up because you didn't touch it. And that is the only product you would get because it is stereospecific. Okay, going to the next problem, this one here. We'll do in this little space here. So we have to draw the chair conformation because we got to get the leaving group in the axial position. So we got two chlorines. This is a locking group, this tert-butyl. So that means it's got to be equatorial. So we'll just go ahead and put it here on this carbon 4. It's coming up. It's most stable in equatorial because it's so hindered. So that is equatorial up. This is axial down. This carbon doesn't have anything. And then this carbon has the chlorine. And so this, if you draw in your hydrogens, this is axial down. They alternate, axial up. And so this would be axial down. The chlorine is going up. So that means it's equatorial up. And then this carbon has the chlorine going up. And because those alternate, the axial down up, that would be that axial up. Now the chlorine that's going to leave will be the one in the axial position. So this chlorine is your leaving group, and your base then will have to take a proton from the neighboring carbon. So if it takes from this neighboring carbon here and this leaves, then you can redraw this and you have your double bond there, and now chlorine is flat. You still have this tert-butyl group going up. So when you draw the two-dimensional structure here, draw your tert-butyl the same way, and then 1, 2, 3, 1, 2, 3, and then your chlorine doesn't have any stereochemistry because it's an sp2. That is the only product you would get. Okay, so now let's look at this last one. I'm going to draw the chair conformation. Okay, so hydrogen's going up. So we're going to put hydrogen going up. There's hydrogen. Let's see. Yeah. Okay. So hydrogen's going up, this hydrogen's going down, and then so to draw the other ring is so bad. We're going to just start all over. Okay, so we draw our chair. This hydrogen's going up, which is that one. This hydrogen's going down, so that's axial down. So this means this one's going equatorial up, this means it's going equatorial down, and then you draw your other chair. Okay, now this carbon here is a bromine, and since this goes down, up, this would be bromine in the axial down, and then this bromine would be axial up. But wait a minute, so you see how this is actually up? So, see if I can erase that, no. So this would actually be hydrogen, and you'd have to make this equatorial up. So which bromine is going to leave when you add KOH? It'll be the bromine in the axial position. So the only hydrogens then have to be in the axial neighboring here. So then this one can eliminate because it needs to be anti-periplanar, and that will actually be your compound here. Okay, we have the same problem with this slide as well. Once again, I apologize. That's all I can do without having to totally start all over. My battery went dead. So we're just going to go through this, and let's just see. You've got vicinal dibromides, and you're using potassium iodide. So you're going to dehalogenate. So you can see here, for this first one, you have the chair conformation. You got a bromine going up and a bromine going down. So this is a chair conformation. Potassium iodide. Iodide loves bromine. So iodide is going to form an iodo-bromo salt. And when it abstracts the bromine, then the bromine's going to, those electrons are going to go and push the bromine leaving group, and you get an alkene. And then to draw the two-dimensional structure outside the chair conformation is right there. Okay, looking at the next problem. The next problem is here. Now you have the bromine on the same side of the ring. So as you can see here, in the chair conformation, you got the bromine above, axial, and equatorial. Now iodide will take this bromine. Iodide will take this bromine, but the problem is this bromine that's equatorial is not 180-degree anti-periplanar. So the answer to that one is no reaction. It cannot happen. When you draw the chair conformation of this compound here, you see that the hydrogen's going up, just like this. So here's your hydrogen going up. You got the bromine going down, so that's the bromine going down, and then you have this other bromine that's going up. And so this one goes down, that one goes up. That's in the 180-degree dihedral angle, anti-periplanar. So that iodide will take the bromine and eliminate to make your alkene here. And I will go ahead and draw that two-dimensional structure. And there it is. And you have your hydrogen still going up like this. Okay, so let's draw this one here. The chair conformation, you got hydrogen going up, you got hydrogen going down. That takes care of those. And then equatorial, this is going equatorial down, this is going equatorial up. And so then you have another chair. And so you have, on this carbon, you have bromine going down. So the hydrogen's going up, and the bromine would be equatorial. And then on this carbon, you have bromine going up. So you can see that your bromines are not in the anti-periplanar position. So could iodide come in and debrominate? Technically, probably could happen because you can actually take syn periplanar, and since they're both in the syn position, but you would have to heat it, and there's a probability you have a low yield. So essentially, you could say there's no reaction. Okay, so predict the products of the following reaction. When more than one product is expected, predict which will be the major product. So if you look at your sheet, you see that this is cyclobutanol, and you're reacting this with sulfuric acid. Now, alcohols are horrible leaving groups, but in the presence of acids like to donate a proton, and when that happens, you get water, and water is a good leaving group. So then with heat, this will leave. So water is a good leaving group. And what happens then is you get a carbocation. And this is a secondary carbocation. And the neighboring hydrogens then will get removed by H. So H2SO4 becomes HSO4 minus. And that is a strong enough base to deprotonate the neighboring hydrogens to give you an alkene. This is always, when you're protonating an alcohol to make water a leaving group, to make a carbocation, this is always E1. And E1 is always Zatsev's product. Okay? So acid, remember we classified the bases to decide whether it was E2, and whether you got Zatsev's product or Hoffman's product. Well, this one is E1 in acid, always. Acid's always E1, you get a carbocation, and you will always get Zatsev's product. Okay? So let's look at this next one here. These lone pairs, in the presence of acid, will get protonated. And the alcohol then becomes a good leaving group. Those electrons will just push off to give you the carbocation. Now your major product, this is a secondary carbocation. So what will happen is you could get a hydride shift here. It's going to give you the same product though. So because it's the base, or the HSO4 minus will come and take that hydrogen away, and you're going to get your more substituted alkene, which is this one here. Okay, the next one here is this alcohol, and you have, is that phosphoric acid and heat. So once again, you have an alcohol. It's going to get protonated in the presence of an acid. Alcohols are horrible leaving groups. They're not like the halogens. And now it's protonated. This is a good leaving group because it's water. When it leaves, it's water. So water is a good leaving group. It's very stable. Now you have a tertiary carbocation. So you've got to look at the neighboring carbons and their hydrogen. And you're going to take the proton by the most substituted, because when you do that, you're going to get the Zatsev's product, which will be the more substituted alkene. So this is a tri-substituted alkene. Show how you would prepare cyclopentene from cyclopentanol. Well, you've been doing this. You just add sulfuric acid and heat. So what happens? This gets protonated, and then that leaves to give you the carbocation, and then your neighboring hydrogen will get deprotonated to give you your cyclopentene. Okay, in the dehydrohalogenation of alkyl halides, so what are we talking about here? Talking about an alkyl halide. We're talking about a dehydrohalogenation. So dehydrohalogenation makes an alkene. Strong base, such as tert butoxide, usually gives the best result via an E2 mechanism. Explain why a strong base, such as tert butoxide, cannot dehydrate an alcohol through the E2 mechanism. Well, look at the alcohol. This is not a good leaving group. It won't leave. So it doesn't matter if you have a base that can take away a neighboring proton. This will not leave. So you have to have an acid, sulfuric acid, and that will protonate the alcohol. And then upon protonation, now you have a good leaving group. And now when the base takes the hydrogen, it can leave. And that's how you get an alkene. So why does a strong acid have to be used for an alcohol? To make the OH into water, because water is a good leaving group. Predict the products of acid catalyzed dehydration of the following alcohols. Okay, this is acid catalyzed dehydration. So the following alcohols: 2-pentanol, 1, 2, 3, 4, 5. We'll just use sulfuric acid and heat. This gets protonated. OH2, which is a good leaving group, and it leaves to generate the carbocation. Always generate your carbocation. Look at your neighboring carbons, and you will always get the Yacht's product. So deprotonate from the carbon that is the most substituted. So that would be your product. 1-methyl-cyclopentanol. So 1-cyclopentanol. Let's just add sulfuric acid and heat. The alcohol gets protonated to make a good leaving group. So show that. And then it leaves to give you a tertiary carbocation. Look at your neighboring carbons of the carbocation. So this is tertiary, you have 3. You want to deprotonate the more substituted. So HSO4 minus will deprotonate the neighboring one to give you this product. Um, 2-methyl-cyclohexanol. So it didn't tell you whether it's trans or not. And it doesn't really matter because you're going to generate a carbocation, and you don't have to worry about the 180-degree anti-pair planar, because that is what you worry about when you're doing SN2 reaction. You don't have to worry about this here because all you're doing is converting the OH into water, which is a good leaving group, and you're generating a carbocation. Now what you do have to think about is the more stable. So in this case, you would get a hydride shift to give you a tertiary carbocation. And then the hydrogen from the neighbor carbon, it's very substituted, will get deprotonated, and you'll get the more substituted alkene product because it's an E1. Okay, the next one, 2,2-dimethyl-1-propanol. So we protonate the alcohol. And then that's a good leaving group. And you get a primary carbocation, so now you're going to get a methyl shift, because that is not your most stable carbocation. So this is your methyl shift. So it switches places with your carbocation. Now you look at your neighboring. This is a tertiary carbocation. This is a primary, so there's only this is a tertiary. You look at your neighboring carbons. the hydrogens. And that is your product. And it's the more substituted, it's tri-substitute. Okay, so let's redraw this one. You want to show the mechanism. And you have a weak solvent, salicylic. So the ethanol is weak. So it's a weak base or weak nucleophile. You have a secondary allylic alkyl halide. Okay, so that produces a nice stable carbocation. So let's go ahead and get our carbocation. And you can see if you have ethanol come in, then you get this, which is an SN1 product. Okay, and it has the hydrogen there, and another ethanol molecule will actually deprotonate that to give you your product. Okay, so this next product here is a resonance structure. So those carbon double bonds can go to that carbocation, and then you get the carbocation here, and then ethanol can come in, and then you get this. So this is still an SN1 product. Or ethanol can deprotonate the neighboring hydrogen, and if that happens, then you get this elimination, which is an E1. Okay, the next problem, you have sulfuric acid and heat, and you have a primary alcohol. So this is going to be an E1. It's going to protonate. So let's look at that alcohol getting protonated. H2SO4. It's going to get protonated. Now the alcohol will be a good leaving group. And when it leaves, you have a primary carbocation. And if actually, just go ahead and not do that one. That one's more challenging, and I'm not going to worry about that. That's ring expansion. We'll just pass that one up. Okay, let's look at this one here. This alcohol will get protonated. The key to these is just to draw them like you see them. So this is 1, 2, 3, 4. 1, 2, 3, 4. And then the OH will leave. So you got a carbocation there. And then this alkene will come here towards that carbocation. You get the 6-membered ring. So this is that one. And this carbon is this one. You got your carbocation there now. And then a base will come and take this HSO4 minus. I'll take that hydrogen to give you that product. So that's an E1. Okay, and then D, basically, you have, this is a leaving group, and when that happens, you get the carbocation over there, but you want a hydride shift. The reason why you want a hydride shift is because this is a secondary carbocation, and if you get a hydride shift, now you have an allylic secondary carbocation. And so if you have methanol then, which is a weak nucleophile, comes in here, then you get the substitution SN1. If the methanol takes this hydrogen away and eliminates, then you get this E1. And if you get a resonance structure here, so if you draw the resonance structure, you draw this alkene moving there, and you get the primary allylic carbocation. And then if you have the methanol coming in as a nucleophile, you get this product here, which is an SN1.